Gonçalves and many others in the crew of the organization of this workshop for their kind invitation. And I also thank your sponsor for making this workshop happen. I also have some sponsors to thank. I just flash their logos. And let me get into the contents of this colloquium. I have arranged it in the following form. First, I will give you some perspectives on near future quantum computers, just to give you the flavor of where we are, and that will make clear that there is a need for quantum error correction in order if we want to make the future happen. And then I will move on to topology in quantum physics. Why is topology so natural in quantum physics? And with that, I will provide you a way to think of topology as a solution to quantum computation. And with that, I will explain some basics of topological quantum error correction by using topological color codes. And finally, I will discuss several experiments with topological color code that are very interesting and very promising for the future of quantum computation. And I will finish with some conclusions. So, regarding the perspective on near future quantum computers, I like to use the following analogy with the evolution of aviation. And in the evolution of aviation, well, there are several steps, important steps, but let me focus on this step by the Wright brothers in 1903, where they were able to fly, to make sustainable a plane in the air for not so long in time and space, but it was enough to convince people that aviation was possible, was starting. It is interesting to see that in less than 25 years, Lindbergh made his famous flight crossing the Atlantic, and that was the starting of the aviation for the whole globe. And precisely what we want to have now is a globe in the form of a qubit, of a quantum qubit, and what we want to traverse all the possibilities of this quantum globe in the form of a quantum qubit. Now, comparing with the evolution of the quantum computer, we have also started with the early stages in which, let's say, around mid-90s, early 2000, people were using basically 1 or 2 qubits, no more than that. And it took quite long to start using more than that, like a few qubits, around less than 10. I think a major change happened in 2016 when IBM launched their IBM Quantum in the Cloud, and then we started to get to know to get familiar with the notion of small quantum computers that were noisy. Or this is the notion of the niche quantum computers, and then what we are trying now to be in a better situation by using the small logical quantum computer. This is what I want to explain. So the idea here is, the question mark here is, when will we achieve a quantum advantage? Well, by quantum advantages, they have several notions. There are several notions. For instance, one is to beat a classical quantum computer, but not in a way that can be useful. So this is something that more or less has already happened but they are useless application. They are academic application in which one can, in principle, use small quantum computers to beat a classical computer. We are more interested in useful application, and even if they are a commercial application. And for that, my opinion, this is something that I already conveyed in 2018 in a conference, is that we will need logical quantum computations. We will need a small logical quantum computer to make something useful. This is my bet. And from that, we will go to large quantum computers and eventually to a large and universal quantum computer capable of doing anything. So we are now living in the era of small quantum computers, and I like to call them baby quantum computers because they are very noisy, like babies. And what that means is that we need error correction to stabilize those noisy quantum computers, those babies quantum computers, in order to have reliable quantum computers. This is the situation in which we are now. We are trying to stabilize quantum computation from these baby quantum computers. For this to happen, it is very important to have in mind the following picture, the following graph, in which usually people think that everything, what the most important figure of merit is the number of qubits. Here in the vertical, I plot the number of qubits, and in the horizontal, I plot the depth of a quantum circuit. So here you have symbolically a quantum circuit in which the width, the vertical, is the number of physical qubits, and the horizontal is the number of gates that you can apply before the system degrades the performance. Interestingly, this is a quantum to classical transition, which is very interesting to study in itself from fundamental reason, not just for quantum computation applications. So the important point here is that people usually think that the number of qubits is what is really important, but it is equally important the number of gates that you can apply before you lose the coherence. And for that, I usually use the following analogy to represent the status of a quantum computer nowadays. And as I am addressing an audience in Brazil, and Brazil is very famous for world champions in racing car, in Formula One, like the famous Ayrton Senna and Nelson Piquet or Emerson Fittipaldi. Let me use the following analogy. I compare a quantum computer nowadays with a car, with a very powerful car, like a Ferrari. So a quantum computer now is like a Ferrari. The reason is because the Ferrari is a very powerful car. It has a roaring engine with a lot of power. However, the point with the quantum computer now is the fact that this Ferrari, when it starts running, it stalls. After racing no more than a few kilometers, it stalls. It gets stuck. And this is the meaning of this horizontal axis. This horizontal axis is the length of the path that the Ferrari can run. And you see that it degrades, so it gets stuck, it stops. So this is a very important message. This is the reason why we need to stabilize the noise, because otherwise we don't have a good horizontal axis here for a good depth, for a good number of gates. If we want to run a quantum algorithm, we need gates in such a number that the quantum algorithm can be implemented fully, completely. So bear in mind this picture with the horizontal and the vertical axis in order to have the whole picture of what we need for a quantum computer to run. Now, following with this perspective, the billion-dollar question for this quantum computation business is the following: is building a quantum computer just a matter of money? Meaning, if somebody tells me I need money, if you give me money, I can build a quantum computer. Is that true? Well, if that is true, then this is an engineer problem, and I am not very interested. It is not very interesting to me. I am a physicist, a theoretical physicist. I am more interested in fundamental questions. If not, as I believe, then there is room for theoretical investigation. And this is the reason why I continue doing investigation in quantum computation, because I believe it's not just a matter of money. It's a matter of doing research, high-level research. Now, there is a clear roadmap to build a quantum computer. It's called the fault-tolerant road. It is painful. It needs a lot of resources, but it is well defined. This is very important. It's well defined. So it is interesting to look for better alternatives explored theoretically. So we have two alternatives: either to implement the fault-tolerant road or to look for theoretical alternatives. Then what to do in this situation? Well, if you are the only quantum lab in the world, if there is only quantum lab in the world, then you can spend your time in anything and you can look for alternatives. But the point is that there are many quantum labs in the world. And if others, if not you, others will go for the fault-tolerant road. So the answer to this question is do both. Implement the fault-tolerant quantum roadmap, but also try to look for alternatives. And in this sense, what we want to do, people in the business of quantum computation, is to look for a quantum advantage with the small quantum computers. And in my opinion, we will have to look for logical small quantum computers with some sort of fault-tolerant quantum computation, fault-tolerant error correction implemented. This was done in the past with quantum algorithms. If we look into the history of quantum algorithms, this situation has already happened. For instance, the Deutsch and Simon algorithms beat classical algorithms, but they were useless, as I said before. Remember when I compared useless versus useful. Soon thereafter, quantum algorithms in the form of Shor, Grover proved superior and useful. So we want to repeat this story of quantum algorithms in the form with the quantum computer, with the quantum hardware. We want to go from the useless applications to useful applications, real hardware. And this talk is about small logical quantum computers. Precisely, this is what I want to advocate as a way to continue with this roadmap for achieving a quantum computer. So now let me move to the following topic. The following session is the need for quantum error correction. We need quantum error correction, as I mentioned before, and this diagram illustrates this fact very well and very easily. Quantum errors may appear statically. You may have qubits that are faulty, gates that are faulty, etc. But the problem is even worse. The problem is that errors propagate in the quantum hardware. Errors are dynamic. They are not just static. They propagate, and that's a big problem. The error propagation in error correction can be seen here. You see in the upper part, you see a block with qubits, logical qubits, physical qubits making a code block. And here you have, for instance, below you have an ancilla, and you apply control gates from the ancilla to the block where the information is stored. Now, suppose that in the ancilla, an X error, a bit flip error happens here. Now, the moment the next time you apply a conditional gate, another X error, flip error, will propagate into the block here. And the moment you start applying another one next, then another error will appear, will pop up. So altogether, a single error due to the environment causes multiple errors in the data. This is the problem of error propagation. Fortunately, there is a solution to this problem, and this is what I mentioned before, as I referred to before, as the fault-tolerant road. This is called the threshold theorem, and the content is fault-tolerant quantum computing is possible, and this is the result of many research. And the threshold theorem states the following: if the error rate is smaller than a certain value called the threshold, then the quantum computation to arbitrary accuracy can be efficiently enacted. In this picture, what I show is the horizontal is this error rate. Error rate could be an error rate in the number of gates applied, on the number of qubits that you have, or in the measurement that you have in your circuit. Now, if you are below this threshold, you are living in an oasis in which you have your quantum computer, and you can run your quantum computer for arbitrarily long times and to arbitrary precision and accuracy. Quantum computation below the threshold is possible. But if you are above the threshold, then everything starts to get corrupted, to degrade. Many errors appear, and you don't have enough time to cope with them, to correct them. Essentially, if you are above the threshold, the rate of errors cannot be overcome with your procedures to stabilize the errors by means of fault tolerant quantum computing. So this is important figure of merit, the error threshold that tells you where you have to be in order to do quantum computing safely. Now, the good news is that fault tolerant quantum computation is possible. This is the good news from this theorem. The bad news is that in practice, the threshold is very small, typically 10 to the minus 5, 10 to the minus 6. This is very bad because, for instance, if you consider it is 10 to the minus 6 in the gates, it means that you have to be able to apply 1 million gates successfully without one error appear. This is a daunting task, and nobody knows how to do that. So these thresholds are very, very small, very low to be practical. Additionally, there is another problem with this, with the construction and this theorem is the fact that the number of qubits scales exponentially because these codes are using concatenation of codes, and concatenation yields an exponential number of qubits. So you have exponential number of resources. The point is very important. A caution here is that this proof of the error threshold is constructive. This is something that I realized back in the time where I started to study error correction. This proof is constructive. There could be better threshold if you improve the construction, removing the concatenation. And this is precisely what topological quantum computation achieves. There is a way out for these two problems, and I will show you later. Now, let me move on to the issue of topology in quantum physics. Why topology appears naturally in quantum physics? First of all, topology deals with continuous, not abrupt deformation. Topology is the study of global properties that are invariant under continuous change, and it is a part of geometry called topology. Here you have an example. You have a layer with 9 holes, so 9 boundaries, plus the external boundary, 10 boundaries. You make a continuous deformation of the layer. You do not change the number of boundaries, either inside or the outside or the outer boundary. So it means that you have preserved the global properties. It means that you have done a topological transformation in this layer, in this surface. However, if you change the number of boundaries, you cut this surface somewhere, then you change these global properties and you are not doing a topological transformation. So, in other words, topology is geometry without measurements, without metric. In topology, the notion of distance, angles, etc. does not exist. This is why you can take a cup of coffee and deform it continually into a donut, back and forth. So topology is only interested in shapes, geometry as a whole, globality. And this notion is going to be very important in quantum computation, as I will show you. In fact, there is a famous aphorism by John Kelly, a topologist, saying that a topology is one who doesn't know the difference between a donut and a cup of coffee, or between a donut and a soother. But a topologist knows a lot about entanglement and surface story. And this knowledge is very good to battle the noise of quantum computers. So why topological effects in quantum physics? Why they appear naturally? Well, this picture tells you why. Here on the above, we have a single trajectory, a classical trajectory going from one point to another point. And this is the result of classical physics. This is the notion of the stationary least action that gives you the single trajectory between 2 points as a solution of the Euler-Lagrange equation of Newton dynamics. However, below we have the path integral picture of Feynman telling you that you have to take into account not just the classical path, but all of them, and weighted with an appropriate phase constructed with the action. So it tells you that you have to explore all the Hilbert space with this path in order to achieve the quantum description of the evolution. In fact, if you cut this many trajectory horizontally, you will see that through that cut there will be a distribution of points. That distribution of points correspond to the distribution probability associated to the wave function. So altogether, what we have with this Feynman picture is that by using quantum mechanics, we are exploring the global Hilbert space of states. And remember that globality is topology. So there are more chances to have topological effects in quantum theory than in classical mechanics. Now, let me show you why topology is a solution to quantum computation. And this is why it is so important nowadays. Well, let me start by saying the following aphorism, the following motto. It's all about getting excited by being boring. Boring. I will explain you why. In fact, topological quantum effect has been known in physics prior to quantum computation, long ago, in the form of topological quantum field theory. And those topological quantum field theories, they were very interesting in the sense that you could do all calculation exactly, analytically, non-perturbatively. So that's a very interesting feature. You can compute things non-perturbatively. But the problem is that those topological quantum field theories, they were boring because they didn't have radiation effect, radiative effects. All the result of computing scattering amplitudes could be written in terms of integer numbers, topological invariant, nothing else. So it was beautiful, but we didn't know what to do with that. So it was a situation in which similar to a solution searching for a problem. So the thing is that problem is the stabilization of quantum computation, in the sense that if we combine topology, this quantum topology, with discreteness coming from an array of qubits of quantum system in the form of a lattice embedded into a topological surface like a donut, then we transform the boredness of topological quantum theories into robustness. So boredness, being boring in these topological quantum theories, become robustness for doing quantum computation. This is the important message that we can relate. We can combine topology with quantum computation in order to stabilize quantum computation, which is the big problem of quantum hardware. Remember that the problem of quantum computation is decoherence, errors, as I mentioned before. Here you have an array, for instance, of ion traps, and you have one qubit, one ion, and you have two metastable states encoding a qubit with 0 and 1. So you are interested in pure coherent superposition states like this superposition, but the problem is that there is coupling to the environment that causes decoherence. For instance, in the form of magnetic field fluctuation, causing dephasing, and this dephasing makes the quantum system run into a classical mixture with phase information lost. All the phases are lost by means of the decoherence. So this means that if you remember, quantum computation can be thought of as the art of taming quantum phases. But if you lose quantum phases because of decoherence and error, then you lose quantum computation. So we have to stabilize this. The problem with quantum computation is that we have more error channel than in classical computation. In classical computation, we have only one channel, the bit flip error channel, flipping 0 to 1 back and forth. However, in quantum computation, we have also the phase flip channel associated to the set error. So this is something absolutely novel for classical computation. And then there was a big challenge how to deal with this, and the computation of the X error and the Z error yielding the Y error. Here, X, Y, and Z correspond to the Pauli matrices. In fact, it was Rolf Landauer from IBM, a famous scientist, who at the moment that Peter Shor came up with his famous Shor algorithm, he addressed him with the problem that if he told Shor, the moment you have one single error in your beautiful quantum circuit of your algorithm, it will spoil everything. And the reason is because of the error propagation that I mentioned before. One single error will propagate throughout the quantum circuit and will spoil all the nice properties of the quantum Shor algorithm. So what Shor did was immediately he put at work and he came up with the first solution to that problem in the form of the first quantum error correction code, and eventually that was the starting point for achieving the quantum the error threshold theorem that I mentioned before. We may wonder, why should we care about a fault-tolerant quantum computer at this point? Why should we care about that? Well, there are basically two reasons. One, on the left, comes from the informatics, from computer science. We are interested in better quantum algorithms like Shor algorithm for prime factoring or Grover's algorithm for database search. And this is very interesting and very important motivation. But as a physicist, I am very much also inclined to discover new physical laws with machines. And remember, we have been physical science, chemistry, all the natural science have been revolutionized with classical computers. Now, the reason why we want to have a quantum computer is we want to continue using better machines to discover new physical laws. This is our expectation. So there is a practical way regarding computer science, but also a fundamental reason coming from fundamental laws of physics, chemistry, etc. So this is a big picture. This is you don't have to forget this in order to have a clear answer to this question. We need a quantum computer, and that's why we need fault tolerance. Well, as I said, topology is a solution to quantum computation. Why? Remember what I said before, the outcome of the error threshold theorem. We had good news, but we also had bad news because of these two features: very small, very low threshold, and large exponential number of qubits needed. Now, the way out to this is topological quantum computation, because topological quantum computation provides you with better threshold, something like four order of magnitudes better threshold, see here, and also the number of qubits you need scales with the size of the system in 2 dimension L square or in 3 dimension L square. So you avoid the exponential growth of physical qubits that you need with the concatenate codes that appears in the error threshold theorem. This is very important to have this in mind in order to understand why topological quantum computation is a solution for stabilizing quantum computations. Now, the last part of my talk, I will revise how to do this topological quantum error correction with topological codes, and finally, I will show you several experiments with topological color codes that were done in the past and now currently, and see the significance of those experiments. Remember that in standard error correction, in classical error correction, in standard quantum error correction, we use extra qubits to encode information. We do an embedding of one single qubit in a set of qubits, which is the block. Here, the simplest one is the three qubits, making the logical qubit. Now, if one error occurs in one of these 3 qubits, what we do is we use stabilizer operators. We measure them, or we apply them, for instance, in between the first 2 qubits. And if we see that this measurement is faulty, we measure the other 2 and if it is okay, then we can deduce, we can infer that there was a faulty qubit in the first place. So what we are doing is to detect error syndrome using stabilizer, and later we actively correct for local errors. We are assuming that the errors are local. In topological quantum computing, stabilizer, we use stabilizer for qubits on a topological surface, typically a torus. Originally, topological codes were introduced by Kitaev in a seminal paper in '97, and I will discuss topological color codes that we introduce later, and the reason is because they provide a complementary way to achieve quantum computation by enhancing some computational capabilities, and also not only about the number of qubits, but also the properties of the quantum gate that you can apply, and very high thresholds. So the idea, following Kitaev idea, is that we will have a code and a discrete arrangement of qubits, for instance, like in an hexagonal lattice with qubits arranged this way. And in general, you don't have to use a regular lattice like the hexagonal lattice. You can use other non-regular lattice, as I will explain before. It is plotted here on the right. And the point is that if one error occurs in one of the qubits, here, around this red loop, the thing is that it will not cause any problem as long as we store information in global properties like this cycle around this handle. So the point is that as long as the errors are local, they involve a small number of qubits, logical information is stored in global system property. This is the nice feature, the beautiful idea behind topological quantum computing. And this is precisely inspired by the movement, by the deformation of the cup of coffee into the donut. Remember that topology is robust global features which are invariant under local changes, perturbation. Those perturbations are the errors. So if these errors, the important assumption is that if noise, assuming that noise and errors are locally, which is a suitable assumption, and actually if you are not able to provide this assumption, it's very difficult to stabilize quantum computation. Then if this is true, then the idea is to store quantum information spread out globally to protect against weak local noise. Here in these two torus, you see here these blue qubits correspond to a local error, and these red qubits correspond to a global loop encoding information, global information, logical information. If this local deformation is applied onto this loop, it only causes a deformation, a local deformation. But the topology of this loop is unchanged, and so does the information stored in it. With this trick, with this important insight provided by Kitaev, we can obtain moderate error threshold, better threshold than in the threshold theorem, and fault and quantum computation might be possible in practice. And we avoid also the exponential number of physical qubits. So this is the critical thinking behind topological quantum error correction. Now, regarding the topological color codes, this is the type, the typical type of lattice, color code lattice. And the reason why these color codes are interesting is because they show higher information storage capacity than in Kitaev's toric code. They have comparably high error threshold, and very importantly, they have improved quantum computing capabilities, almost universal in 2 dimensions, universal in 3 dimensions, and they implement transversal gate set, which is something very useful. Remember that for doing quantum computation, we need a quantum compiler corresponding to a set of gates that are universal. A universal set of gates correspond to the Hadamard and the T gate, but you can also find a Clifford group implementation of quantum computation if you use this T square or K gate here. This is the CNOT. And in 3 dimension, this can be extended in the form by using the appropriate gates. In particular, for the color code, what we can do in 3 dimension is that we can implement directly the T gate, the square root of K, which is the T gate here, along with the CNOT, and along with transversal measurement of X and Z operators. So in 2 dimension, we can implement robustly the Clifford group, and we can obtain a universal quantum computation by means of additional resources like magic state distillation. But in 3 dimension, we can avoid magic state distillation and use and implement T gates directly by means of this transversal measurement. So altogether, the reason why we came up with the idea of color codes was the idea of combining transversality of gates with the topology of the qubits. And remember that a gate is called transversal if you apply the logical gate in the way that you apply the physical gate. That is, if you need to apply one single gate logically at the logical level, you apply it also bitwise, bit by bit, qubit by qubit. Like here, suppose you have a unary gate, you apply it tensor-wise. So transversality means tensor-wise. If you have a 2-qubit gate like the CNOT gate, then you have to do it tensor-wise. The first with the first, the second with the second, and so on and so forth. What you gain with this is 2 things. In this way, you stop propagation of errors. This is very important property. And second, this is a type of transversal gates are very amenable for experiments. Experimentalists love transversal gates because they make life very easy. They don't have to devise intricate patterns of logical gates in order to obtain the logical gates from the physical qubits. They don't have to provide intricate patterns of physical qubits to make up a logical gate. It is very simple. Transversal gates is what you see, is what you get. You want to apply a CNOT, do it physically, and you will get a CNOT logically, and so on and so forth for all the gates. And this is what color codes provide you. So the picture of a quantum error correction code, in particular a color code, is that instead of having a string of qubits like a standard quantum computation, you have a register stack. You have a stack of layers. Each layer is a color code, for instance, and you can implement 1-qubit case by means of external lasers or 2-qubit case by means of external lasers involving 2 qubits, and so on and so forth. So you have to enlarge the spatial dimension. This TO is a topological order, for instance, in the form of a color code, and then in that way you get a register stack that is your quantum computer. It's not the only way to do that. There are other ways of implementing topological color code by using one single layer, but today I will not talk about that. This is a colloquium for an introductory level. This is enough. So in more detail, the definition and fundamental properties of color code are the following. Here you have a color lattice with 3 colors, red, green, and blue. You have also edges with also the 3 colors, red, green, and blue. So they correspond to stabilizer quantum error correcting codes. They belong to the same family. They are defined on trivalent 3 colorable lattices. It means that each vertex has 3 links, coordination number 3, not 4, like in the Kita F code. Importantly, Qubits are located on vertices of the lattice, not on the edges, like in Kita. And the stabilization operators are plaquette operators, only plaquette operators, not vertex operators, like in Kita, only plaquette operators. And they come in two flavors, one for X and one for Z, for the bit flip and the phase flip operators. Here, for instance, the reason why it's a color code is because one plaquette, if it is red, it is surrounded by plaquettes with the other two colors, not by the red, and similarly for the rest of the faces. Equivalently, this corresponds to having three colors for the edges. Why does this color structure appear? The reason is because in this way all stabilizers commute, and this is a fundamental property for stabilizer operators. And the second reason is because it allows us to implement gates transversally, as I said before. So the picture of the Hilbert space in this case is the following: as the stabilization operators commute, you can label subspaces of the total Hilbert space of states by these eigenvalues of these operators, and only the subspace corresponding to +1 eigenvalue for all the stabilizers that correspond to the code space where we store the information. We can describe physically this code space as the ground state of a Hamiltonian operator corresponding to the superposition of the plaquette operators, of the stabilizer operators of the color code. And it's a nice picture because it's a physical picture. As a curiosity, color codes can be defined transversally. Translationally invariant and there are only three families: hexagonal, this 488 code, and this other one more complicated with this 12-sided polygon. No more than this. But as I said, you don't need translational invariant. It is enough to have a color code with an arbitrary lattice structure. This, for simplicity, I will use the honeycomb lattice, the hexagonal lattice, because it's more easy to illustrate. So here I have a color code with the hexagonal lattice. Remember that each plaquette carries two plaquette operators, two stabilizer operators, one with the Z Pauli operators and the other one with the X operators, Pauli operators. Now, in order to combine this flat lattice into a torus, we just have to glue to identify vertical sides together and also the horizontal boundaries together. And in doing that, we achieve the torus that I have there in the upper bottom, in the upper part. Now, with this, I can construct logical operators that encode the logical information, the logical qubits, and I do it in the standard way. I can apply a string of Z and X operator going from one side to the another, which correspond to this loop, this blue loop here above, because after the identification of the boundaries. And I can construct the dual logical qubit for the Z and the X by doing the same with a string that goes now from bottom to up through the color plaquettes. So I use a blue plaquette horizontally and vertically a red plaquette. So in this way, I have two qubits, two logical qubits. This is what happens with the key-type code. The interesting thing is that with the color code, we can even double this capacity because we can also use a horizontal blue string of operators and a horizontal red string of operators and vertically a string of blue operators running through the qubits of these blue plaquettes. So altogether we have 2 plus 2, 4 qubits, 4 logical qubits for this torus. In the case of Kita F code, we have only 2 logical qubits. Here we have 4. We increase the storage capacity. You may wonder what happens if I do the same thing with the green, because I have the other color, the green. Why don't we do the same thing with the green? Well, the reason is because this structure has some constraints, and in particular, if I do that with a green string of operators, it so happens that the green string of operator is not independent. It can be reconstructed out of the blue and red strings. So only 2 colors are independent. You can choose either one from the 3. Here I have chosen red and blue, but I could have chosen any other couple of colors out of 3. This is very important. Now, how error correction is done here? Well, in color code, suppose that you have an error occurring in this qubit, a phase flip, for instance, sigma z. Well, if you measure the dual stabilizer operator, the X stabilizer operator, in the surrounding plaquettes, you will see that it has a -1. It is faulty, and that will detect a flip phase error in this qubit. Similarly, if the error is a bit flip error, an X error, by measuring the surrounding plaquettes for the dual operator, you will get a -1. So this is the way to, by measuring syndromes, we obtain a pattern of errors, and then we can correct with appropriate external operations. The picture of this error correction is the following. We have the whole Hilbert space. The code space is the one, as I said before, corresponding to all +1 eigenvalues of the stabilizer of the plaquette operators. Now, the moment an error occurs, like here in the left figure, it means that the code space, the state goes from the code space out of it. It goes to the error space. And then by measuring the syndromes, we detect that error and bring it back to the code space by means of the error correction. So physically, what we are doing is that errors correspond to hitting the system. You think of the system, the code space, as a ground state, and the error correction corresponds to the opposite operation, to refrigerating the system, getting back to the code space. If we continue comparing this color code with the Kita F code, there is a clear signature, a clear difference between the pattern of errors that appear in one system and another. The errors that may appear in the Kita F code are only of error string. You have only a string with 2 endpoints. In color code, we have these errors, but the principal errors correspond to string nets. So this is a branching point in which you have a string with a branching point, and you have 3 ends instead of 2. These are not only errors, but also they can be useful. They can be used to produce logical qubits. And this is a distinctive feature of color codes that is not present in Kita F codes. It's a way to say that strings in the color codes are more interacting in strings than in Kita F code, which are simply two-ended strings. So the error correction goes through is about to guess from the measured error syndrome most probable physical error scenario and derive a good recovery operation, as I said before. With this, it is very interesting that we can compute error threshold for color codes, and with only qubit errors, we achieve the same 10.9% of error threshold as in the Kita F model. If we consider also measurement errors, it gets smaller, but not much, basically 1/2, 4.5%. And in more realistic scenario, we can keep very high thresholds. So these topological color codes are very good candidates to do quantum computation. And to show that, let me finish by showing some experiments with topological quantum computation performed with color codes. The first experiment was done by my group in collaboration with the group of the professor Rainer Blatt in Innsbruck 10 years ago. So the first thing that we have to do is that we have to change the torus with something more practical, because you arrange qubits into a torus and experimentalists will not be able to do that. Experimentalists in a lab, you cannot do these torus with the qubit. You have to come up with something else. Fortunately, in our original paper, we describe how to do that. And it is by the following. Instead of considering a torus, consider a sphere and remove one qubit from the sphere. And then from that qubit start opening up the boundaries and flatten out the corresponding flat surface onto the plane, and you will get this triangular code, a triangular code in which you have the three colors at the boundaries of the three boundaries of the triangle. And the reason is because the moment you remove one qubit in the sphere, you are also removing three faces, and each removed face, the color of each removed face appears at the boundaries in green, red, or blue. Right? The difference is that if in the color code on the torus we had 4 logical qubits, here we have 1 logical qubit instead of 4. But it's fine. It's fine because it is robust, and we can implement logical operator in the form of string nets or transversal gates. So this is the way to convince an experimentalist to do an experiment with color codes. And this is what I did in 10 years ago with a group of Rainer Blatt, to convince them that they could do this experiment in their lab. And this the way to convince is to use the minimal color code, the minimal triangular code possible, which is this one made up of 7 qubits and only three plaquettes. So altogether we have 7 qubits. We have each plaquette carries 2 plaquette operators, 2 stabilizers. Altogether we have 6. So the number of physical qubits is 7. The number of constraints is 6. 7 minus 6 is 1 logical qubit. The logical operators here are written transversally, 1 tensor-wise each of the qubits in the 7 qubits in this plaquette, and we can check that the Pauli algebra is realized by means of this construction of the minimal color code. This is the team. The theoretical team was Markus Müller, then was a postdoc in my group and myself, and the rest of people is Rainer Blatt from the laboratory in Innsbruck, and his team of collaborators. Here is the team working in the lab, usually overnight, and this is the string of qubits in the ion traps. This is the ion trap here. Here they are very happy because things were running well. Sometimes they were not, but eventually, working hard, they were able to perform the experiment. This is a close-up of the experimental toolbox. The ion trap designed by Rainer Blatt is very particular, you see, and this is the size. You can guess the size of this ion trap comparing with a coin of €1. So this is the scheme. They use is the same scheme as in the Sirac-Soler proposal for ion trap quantum computer, using ion calcium and the scheme of 3 levels, 2 for doing the qubit manipulation, the 0 and the 1 in this scheme. This has a decoherence time of the order of seconds, and they use an additionally level in order to monitor the detection of the qubit, whether it is in the low or in the upper level. This the time the lifetime of this of this detection scheme is of the order of nanoseconds, so they can monitor permanently the qubit without any further problem. They have in the lab or in the Innsbruck lab, the blood group, they have a toolbox. They have a toolbox that they have developed over the years, so they can implement with laser. They can implement single gates by addressing transversally the qubits, or horizontally. They can also introduce collective spin flips, and also they can implement entangling gates similar to the CNOT gate necessary for universal quantum computation. With this toolbox, they can implement universal operation. The point is that they are not protected from noise, and this is the reason that they were interested in using our color codes in order to protect this gate set and make it into a topologically protected gate set, universal gate set. So what we had to do is to map the minimal color code in the string of 7 ions, and with that everything prepared. Well, we did the experiment and the analysis, and we wrote these two papers, one in Science and the other one in Physical Review X, in which we did 3 things altogether: encoding, detecting errors and syndromes and correcting them, and also logical operation. This is very important, the 3 things together. So the error correction, the encoding was achieved by using these schemes that they have. We started with the states 10101001, which is an eigenstate of the set stabilizer. This is something very easy to do because they correspond to one single gate. And starting from that and using the entangling gates that I mentioned before, they were able to implement the red plaquette by means of a cat state involving 4 qubits, the 4 qubits of the plaquette. Then doing the same thing with the blue and the red. At the outcome, we obtain the logical 0 state corresponding to the minimal color code, and this is protected. So we have 7 physical qubits unprotected, and we make it into one single qubit protected. How were we sure that this was done properly? By measuring the syndrome. And measuring the syndrome corresponding to the red plaquette, we saw that the 2 stabilizer for the X and Z stabilizer to the red plaquette, they were flagged up. Then, after doing after imposing the blue plaquette constraint, we measure the two plaquettes, the 4 stabilizer corresponding to the red and the blue, and they were flagged up as well. And similarly for the green, by measuring, we saw that the 3 plaquettes had flagged up the stabilizer corresponding to X and Z. Here you see that in the red we have 2 spikes corresponding to a cat state. Then with the blue we have now 4 states here, and with the green we have 8 states. By the time this experiment was run, this was the most complex quantum state ever produced in the lab. We also did error detection and correction. We induced errors in some of the qubits in this minimal color code. We detected that we checked that these errors were properly applied by measuring the syndromes. And lately, we corrected them. We detected and corrected them. And we checked that the error correction can be properly carried out once the minimal color code was built up in the first stage. And finally, we also did logical operation, and this is very important, and especially in the context of nowadays developments. What we did is the following: we have one single qubit, logical single qubit corresponding to this block sphere, and what we did is to perform logical operations, one single gate at the logical level, and checking that they were implemented correctly by measuring the syndrome. And this is very important because when we run this several times, a chain of logical gates applied one after another, we saw that we were able to sustain up to 12, 14 gates before the coherence took place. This is what I mentioned before when I was talking about the Ferrari, when I was talking about the horizontal axis in the quantum circuit, the depth. We were able to have a depth, non-trivial depth. And this was something for the first time, because before people apply one single gate, and after that single gate, the system was destroyed. The coherence of the quantum system was destroyed. Here, it was sustained, it was maintained, it was kept thanks to the topological features that we had implemented in the encoding. And this is very important. This is a way to show that topology can be a solution for quantum computation. Now, this was about our experiment, but I also want to comment other people's experiment. For instance, the key-type code was implemented later by IBM in Jay Gambetta's group, and also in Google by the Martinez group. It's important to remember that topological color codes are device independent. You can implement them in any device. We started with the ion trap, but in principle, you can implement it with superconducting qubits, with silicon qubits, with photonic qubits. In fact, with ion traps, the laboratory of Rainer Blatt, they have a spin-off company called Alpine Quantum Technology, and they continue developing quantum computers using this architecture. Recently, more experiments have been conducted by a new company, Quantinuum, which is related to Honeywell. And for instance, they have been doing also with ion traps, they have been implementing quantum error correction, and they have compared color code with the 5 qubit code, and they have checked that color code has better properties. More recently, there is a result involving neutral atoms, not ions, but neutral atoms, by the Quera company, which is a spin-off of the group of Misha Lukin in Harvard, and they have been using color code properties in order to obtain 49 logical qubits. This is really amazing. 49 logical, not physical, logical qubits. This is what I mentioned before, is you don't have to be impressed by the number of physical qubits. What is really impressive is the number of logical qubits. And these Quera companies are using color codes. They have a roadmap to achieve in 3 years, ending by the end of 2026, they want to achieve 100, not 49, but 100 logical qubits, universal, built up from 10,000 physical qubits. And with 100 logical qubits, you can start thinking about doing non-trivial things, right? And they are using these neutral atoms and the ideas of the color codes. So this is very promising. I think this is very, very important and interesting. Also, the Continuum company that I mentioned before, they are doing experiment with color code, and they have done quantum teleportation between the minimal color codes. In fact, quantum teleportation has been subject of a patent, in a US patent for color code for doing teleportation. And this is a patent that was was subscribed by Amazon Technologies. In the group of Reinerblatt, they have continued using quantum ion traps in order to advance the result, the experiment, and they have constructed CNOT gates involving CNOT gate involving two logical qubits, one for the target and the other one for the objective. Sorry, for the primary and the target qubits. They have and there are more developments using these color codes and in combination with others involving ion traps. Here there are other very interesting results for coping with qubit losses and using lattice surgery. So these are the conclusions. Coming back to this picture, remember that it's not just about number of physical qubits. It's very important the depth. This is why quantum error correction is so important, because you need a number of a high number of gates applied robustly in order to implement the quantum algorithm. So without high thresholds, the quantum computer will not fly. We need high threshold in the context of quantum error correction in order to make this happen. And we are, I think there are very interesting advances in this direction nowadays, and there are ongoing plans to continue with this roadmap, this fault-tolerant roadmap. Let me mention that three-dimensional color codes are a very interesting option because they provide you with a T-gate factory. We proved this long ago, and we proved that in 3 dimensions we can have a universal quantum set of gates providing a T-gate factory without having to implement magic state distillation, which is costful. And well, the idea is that instead of using the triangular planar code, you use a 3-dimensional pyramid or tetrahedron. This tetrahedron, this elementary tetrahedron, contains 15 qubits instead of 7, 15, and arranged in a proper way with volumes, color volumes. Now we have 4 colors instead of 3. Incidentally, people have patented these 3-dimensional color codes for doing this T-gate factory. For instance, this is a US patent by STM Microelectronics. There are also patents for doing error correction with these 3D color codes. In this case, this is one by Amazon Technologies. So let me finish by thanking my collaborators over the years. For color codes theory, Hector Bombín, then was my PhD student in Spain, Professor Helmut Kalgraver and his student Ruben Andris, and Masayuki Oseki for the analysis of errors in these color codes. And for the experiment, the color code experiment, my 2 postdocs by then, Marcus Muller and Angel Rivas, and Professor Rainer Black and his group, who did this dream come true, because it was really an amazing challenge, and they were able to find the tools, the ways, the experiment in order to produce these beautiful experiments with color codes. And with that, I finished thinking really that the best is yet to come. But for now, this is it. Many thanks for your attention. Thank you.
Thank you. So, Miguel, can you take some questions right now?
Yeah, I can.
Okay.
Actually, I didn't know the length of my talk, so I don't know whether I was running out of time but as we
no problem.
started,
No problem.
Okay.
We are in Brazil. So let me move to the audience here. A little bit dark, but and there is the audience in the YouTube also. So, so is there any question? Clarice Albuquerque is going to make a question.
Hi, Professor Miguel.
Hi, hello.
I'm Clarice Albuquerque. My question is about anionic computing.
Okay.
Is anionic computing still an interesting proposition? Or what are the
Yeah.
perspectives
No, no.
for the physical
Well,
realized of?
this is a very important question. I didn't have time to explain that topological quantum computation has two big avenues. I have explained one of them using ground state properties, but there is another one using excited state properties. These correspond to anions. These anions, they have braiding properties that allow you to implement unitary operations robustly. The problem is that just to produce one single anion, like in a Majorana anion, it has turned out to be very, very difficult. And we don't have yet an experiment with one single topological qubit of anion type. The type of topological qubit that I mentioned before, they are topological because of the ground state. But for the excited state, experimentally, theoretically, the problem is solved. Theoretically, but beware that even anions, they have errors, and they have to do error correction, even with anions. And it is not trivial. But the main problem is that experimentally, we have not succeeded in making one single topological qubit with anions. And it is so important, that question, that producing anion experimentally, it's important in itself as a fundamental question, as a new quantum phase of matter. If the moment somebody is able to clearly produce an anionic system, that will be a Nobel Prize, without doing quantum computation, just to produce clearly. And clearly means seeing experimentally the braiding properties of the anions. If somebody is able to do that unambiguously, clearly, that's a Nobel Prize. That's a breakthrough. Once you do that, you will need still to produce big braidings, in order to run a quantum computation. So I think the type of topological quantum computation that I mentioned in my colloquium is much advanced experimentally than the other one. But as I also said in my colloquium, we need alternatives. We have to be open to alternatives, right? And this is important. The quantum computation is not yet an engineering problem. Fortunately, there are a lot of engineers working very well, but still we need theorists. We need theoretical solution to help experimentalists to produce quantum hardware. Anionic quantum computation is an alternative, but it is delayed experimentally because of this problem of producing them. Let me just mention one thing. Majorana fermions, Majorana anions, if they are produced and used for quantum computation, the power of a Majorana quantum computer is the same as the topological color code. They produce Clifford quantum group in 2 dimensions. With Majorana, you cannot obtain universal quantum computation. With color code, you can obtain universal quantum computation if you go to 3 dimensions. I think, Clarice, I think we never met, but I think you work with Eduardo Brandani.
Yes.
Okay. I am very pleased to send you my best regard to, because that group has been doing a very nice work on the hyperbolic color codes, and
Yes.
exploring the possibility of hyperbolic geometries to construct new color codes and new thresholds. I think that's a very interesting work. I think there is room for making more progress in that if you go to 3 dimensions.
Hyperbolic color codes, it's not my work. I did the topological quantum codes with genus greater than 2, but the toric code, G-torics.
The toric, sorry.
But
I thought you were a collaborator.
I understand the generalization of hyperbolic color codes to genus greater than 2.
Mm-hmm. Okay.
We found MDS color codes with genus G greater than 2.
Okay, good, very good.
So just a quick question from myself. So there are people from industry here in this conference. And so you said 100 logical qubits by 2026.
Well, this is. Yeah.
Wait a minute. Let us see if we are speaking the same language. Logical qubits means that you have implemented concatenated codes. Oh no, only one. Yeah. So clarify that. 100 logical qubits seem very impressive for 2026. What do you know about that?
Okay, so maybe I was too fast during my talk. This is a result, a very recent result by the company Quera, that is a spin-off of the Misha Lukin group in Harvard. Right now they have produced 49 qubits, logical, not physical, logical. And in this company they have a roadmap of continuing using. They are using not ion traps in this case. They are using neutral atoms. They are using optical lattices. They are these lattices made of light, in which the atoms, the neutral atoms, they are placed in the valleys, and with laser they can put them into interaction and create gates and quantum computation. Well, they have been using the color codes ideas in order to encode information in logical qubits. So they have a roadmap. You can visit their website, and they have the target of producing 100 logical qubits out of 10,000 physical qubits. The reason is because in an optical lattice you can populate many, much more physical qubits than in an ion trap or superconducting qubits. In an optical lattice, you have access to populate that with thousands of qubits. In this case, the qubits are neutral atoms, not ion, neutral atoms. And because of this reason, because of the structure of the optical lattice, they are able to produce much more logical qubits by the number of 100 by the end of 2026, using these color codes and concatenation. Codings. There is no concatenation. Concatenation, forget it. Concatenation, you cannot use it. It's not practical. You cannot use concatenation. You have to use topological codes. Concatenation ruins everything. It's important theoretically, but not practical. So with these optical lattices, they plan to reach 100 logical qubits universal by the end of 2026. And they will need of the order of 10,000 physical qubits. is this, remember the example of the triangular. The triangle that we did experimentally, the number of physical qubits is 7, but the logical qubit is 1. Now, what they are doing is like constructing 100 logical qubits with 10,000 physical qubits. So they are using encoding, the encoding of color codes to do that. No concatenation. Concatenation is not practical.
Yeah, I understand now. So, I thank you for your listening from your point of view of quantum computing. It is really interesting and very enlightening. So we thank you a lot for your talk. Thank you.
Thank you. I just want to send my best regard to the Brazilian community. I know some of them, either personally or by their jobs and their works. And I'm sorry not to be there, but I hope that we can keep contact and scientific contact, because I think it's very, what you are doing there and with this workshop is very, very good, and is very very interesting for developing and pursuing quantum computation in Brazil and in Latin America. Congratulations to you all.
We hope you can come next time, maybe next year or in 2 years.
Very
good. Okay.
Hope
Thank you a lot. Bye now.
Bye-bye.
Okay, so